Hello, this is a video for EDX Statistics 1. It is the second video in this series and it will look at the binomial distribution. To begin with, we're going to consider what a random variable actually is. It's a variable whose value is subject to variations due to chance, and it can take on a set of possible different values, each with an associated probability. They're useful usually due to representing possible outcomes of a yet to be performed experiment or possible outcomes of a past experiment. An example of a random variable is the score you get when you throw a fair six-sided die. We tend to use a capital letter to stand for the score, so a capital X in this case. X would be considered to be the random variable. And X can take the values 1, 2, 3, 4, 5 and 6, and the probability of each of those outcomes is known, and in this case is 1/6. We consider this variable to be discrete because it can only have these 6 integer values, not ones in between such as 1.5 or 2.9 or anything outside of it like 7.2. Later on we will look at continuous random variables as well. As I said earlier, we use a capital letter for the random variable itself and then the same small letter for the values it can take. So lowercase x would be 1, 2, 3, 4, 5 and 6. When we talk about a probability distribution, we talk about a model that is used to give the probability of each value of the random variable occurring. So this table in the middle here represents the probability distribution for the previous example of rolling a fair six-sided die, where each outcome is listed and next to it is its associated probability. This would be considered the probability distribution of X. In this case, it has a special name, the discrete uniform distribution, and that's because every probability value is the same. In this case, we can summarise this as the probability of any score on a dice, capital X being any particular value, lowercase x, to be 1/6 for any value from 1 to 6. We're next going to look at a binomial model. And this is an example of a binomial model. We're going to roll that same fair die 4 times, and we're going to record the number of 5s that we get. We want to know the probability of getting different numbers of 5s. Now clearly we're rolling it 4 times, so we could get no 5s up to 4 distinct 5s. Now this is what makes it a binomial model. We have 2 outcomes, a success or fail. We have a series of independent events, a constant probability of success, and a fixed number of trials. And these are considered to be the conditions of a binomial model. So we can just talk about a binomial model by its parameters, that is to say the probability of a success and the fixed number of trials. And if we say these 2 things and tell people that it's a binomial model, the other parts of the model are given. We can write this in shorthand by saying that y is binomially distributed with parameters n and p, saying that in this form. So in our example, y, the number of 5s we get rolling a dice 4 times, is distributed binomially with n is 4 and p is 1/6. Now we could draw this out as a tree diagram. So we have 4 rolls of the dice, and in each case you either roll a 5 or you don't. The probability of rolling a 5 is 1/6, and the probability of not rolling a 5 is 5/6. And we want to know the probability of getting different numbers of 5s by the end. So the outcomes look something like this. The top one here, where we roll 5 after 5 after 5 after 5, I've written like this, and so on. This is 3 5s followed by not getting a 5, and so on. Now, what's interesting to note here is that the probability of getting 3 5s, for example, and 1 non-5 is the same whether you get the 3 5s first, followed by not getting a 5, or 2 5s, not a 5, and then a 5, or a 5, not a 5, and then 2 5s in a row, or failing to get the 5 first time and getting the 3 5s later. And all of those 4 different ways of getting 3 5s will have the same probability. And that's the same for getting 2 5s and 2 non, or 3 non and 1 5. And then there's only one way of getting 4 5s and one way of getting no 5s. So I can summarise those probabilities like this. So I've got 5 6 to the power 4. There are 4 different ways of getting 1 5, much as there were 4 different ways of getting 3 5s. There were in fact 6 different ways of getting 2 5s and 2 non-5s, and this is where the probabilities are. So we can turn this into a formula which looks like this. So we need to know how many different ways something can happen multiplied by the probability of success to the power of the number of successes that there are. So here we've got probability of 1/6 and we had 4 successes, times the probability of a fail, which is 5/6 here, to the power of the number of fails. So if you consider this one, I've got 4 different ways it can happen. Probability of success 1/6 to the power of 1. The probability of fail 5/6 to the power of 3, which is the number of fails I've got and the number of non-5s I've got. And that can be generalized to any binomial distribution, where NCR is the number of different ways of getting your particular outcome. Now we need to know how to find this number. So in the previous slide it was 14641, and there's several different ways you can get this. You can either get them from the tree diagram like we've just done, from Pascal's triangle, which I'll show you in a moment. You may have a calculator with an NCR function, or you can use a formula, which is n factorial over n minus r factorial times r factorial. Here's Pascal's triangle as promised, and there's the row that was 14641, and you could just read that off. So if you had 6 trials in your binomial, you could look at this row of it as well. But in practice, we generally don't have to use the formula at all, because you will need a calculator that can calculate these probabilities in the exam. So a calculator will calculate it. You can also use GeoGebra or other statistical packages in order to calculate these things. So you can see here on the screen, I've got a binomial model where n is 4 and the p is a 1/6, and I'm looking at the probability of being greater than or equal to 2, and there it's worked out the 3 probabilities, 2, 3 and 4, and added them together to give me 0.132. So here is an example. You may want to use your calculator to find these, so if you want to do that, pause the video now before I run through the answers for this example. So in an experiment, a bias coin is thrown 8 times. So we have a binomial distribution with n is 8. It's a bias coin, however, so the probability of getting a head is 0.3. We want the probability of getting fewer than 4 heads, exactly 5 heads, and more than 3 heads. So the first one. We have a binomial model of 8, 0.3, and we're going to calculate that probability using a statistical package here, which gives us 0.8059. Exactly 5 heads. So I've included the formula here, as it could be done on the formula quite quickly as well, but you can see I've calculated this from the statistical package here. The probability of being from 5 to 5 is 0.0467, and you can see there it's the same with the formula. 8 choose 5 times 0.3 to the 5 times 0.7 to the 3, and that gives you this number here. The last one, more than 3 heads, So here I've got the probabilities from 4 to 8. Now if I was to do this with the formula, I'd have to work out 4, 5, 6, 7 and 8 with the formula and add them all together to get this answer of 0.1941. Some calculators only give you the probability that x is less than or equal to something, so you'll have to work out the probability that x is less than or equal to 3 and subtract that from 1. That's the end of this video. The next video in this series is on hypothesis testing in binomial distribution.